This video goes over how to calculate X bar and R charts to determine if a process is in control. It's also used to show you how to calculate process capability using the DPMO statistic. So here's some data. We have tread wear, where we measure 3 observations per sample, and we got 30 samples. The first thing I'm going to do is calculate my sample average and my range. So for every sample, I'm going to go calculate sample average and the range. There's no range function in Excel, but there is a max and a min, so you can use that to calculate the range. Next thing we're going to do is go grab our constants. The observations per sample is 3. We need to calculate X bar bar. The average of all of my averages. Calculate R bar. The average of all of my ranges. To calculate control limits, I need to know what the constants A2, D3, D4, and later on we'll use lowercase d2. Where do I get that data? You can do a Google of control chart constants. So A2 is 1.023, D3 is 0, D4 is 2.574. 1.023, 0, 2.574. These are constants. I'm also going to need lowercase d2, 1.693. From these, I can go calculate my control limits for my 2 control charts. So the upper control limit for the X bar and the lower control limit for my X bar. The formula for the upper is X bar bar plus A2 times R bar. Put some dollar signs around all this because we're going to copy them down. I want the same number. For the lower control limit, it's exactly the same thing, except instead of plus, it's minus. Take those, copy down all the way for all samples, and then you can calculate or produce your control chart by grabbing your sample averages, your X bars, and your control limits, and using the line chart. The first one is cleaner, so that's the one I'm going to use right there. So there you go. So based on the sample averages, your process is in control. But we're not done. We also have to calculate the upper and lower control limits for the R chart. The upper control limit formula is equal to D4 times R bar. These are formulas in the book. The lower control limit is equal to D3 times R bar. Again, a formula in the book. Grab those, copy them down, and then go grab your R's and your control limits. Build another line chart. Usually what we wind up doing is putting these right below each other. We'll scoot over here. Zoom out a little bit. There's my X bar. Here's my R. We like to stack them on top of each other so we can kind of see them on the same time slice. And there's your process, and we can see right now that the process is in control. We're not outside the control limits on the X bar or the R chart. So once the process is in control, now we can start determining if the process is capable. And what we're going to do is we have to compare the process, not the sample, but the process to the customer requirements. So for this problem, the customer requirements is that tread wear should be between 15 and 45. And that's an input. So these are inputs. You don't calculate them. They are given to you from the customer. So both of these are input. So I'm telling you that the upper and lower spec limits, so these are specification limits. I need to make sure that when I produce a tire, the tread wear should be between 15 and 45 is what I'm saying. If it's outside of that, it's not a good tire. So now that I've got this, now I can start looking at my data. So I need to know what is my process average, which is mu and sigma. I need to know what my process mean is, and I'm going to go ahead and make that a Greek letter. Same thing here. I'm going to make it a Greek letter. So I need to be able to estimate what is my process mean and my process standard deviation. Well, my best estimate for the middle is just X bar bar. That's my best guess. My best guess for my standard deviation is actually equal to R bar sample average, the sample range average divided by D2. But all that, we don't want that in Greek. Put that back just in your normal font. There we go. So how do I calculate that? Well, it's R bar divided by D2. So now I've got a process center. This is based on the data. My process is 31, the average, and the standard deviation is 6.5, and I'm going to assume it's normal. So now that I've got a process centered at 31 with a standard deviation of 6 that's normal, and I've got my requirements, I can determine the defects to the right, defects above the upper spec limit, and it's just equal to 1 minus norm dist. You put in your upper spec, you put in your mean, you put in your standard deviation, last argument's always 1. And then the area of the defects below the lower spec limit is equal to norm dist. You put in your lower spec, you put in the mean, the standard deviation, last argument's always 1. So both of those, so I've got about 2% of the stuff above spec and less than about 0.5% or 0.4% below the lower spec. So the total defects percent or area probability is just the sum of those. Now, a new term is the defects per million opportunities. That's going to be equal to this area multiplied times a million. So that's the number that we would report. That's the number that we would report is our process capable. If someone said, what's your process capability? What you would answer is that my defects per million opportunities, DPMO, is 23,000. The starting point for goodness is usually 2,700. So a good DPMO is less than 2,700. So I would say right now our process isn't very good. We're not nearly under that. Okay, that's how you calculate control charts, and then when a process is in control, determine if a process is meeting customer requirements by calculating DPMO. Thanks.